Let C be the parametric curve of the plane with C of t equals 2 cosine of t comma sine of t multiplied by parenthesis 1 plus 1/4 multiplied by cos of t, with t into the closed interval from 0 to 2 pi. Our goal is to show that curve C is a smooth, simple, closed curve and afterwards, to find the area of the region enclosed by the closed parametric curve. Observe the given figure and try to understand how, for any t0, in the closed interval 0, 2 pi, we calculate the x, y Cartesian coordinates of the point A, on the parametric curve C. From calculus we know that if capital F is a continuous and differentiable function on the closed domain A to B, then the area of the range enclosed by the graph of function capital F, the axis of x, and the lines x equals A and x equals B, is given by the definite integral of capital F function over the closed interval of A to B. Assuming of course that f of x is bigger or equal to 0 for every x in the closed domain A to B. In the given figure you can see the region under the graph of function capital F. Now let C be some parametric curve of the plane with x coordinate some function f of t, and y coordinate some function g of t, with t, into the closed interval t1 and t2. Now, the question that very logically arises is if one could use the same big idea in order to calculate the area of the region under the parametric curve C. But as we did before, for function capital F, demanding to be differentiable on the A to B domain, we firstly have to establish some essential conditions for the curve C analogous to the ones we did for function capital F. In order to find the area of a region under a parametric curve, the curve needs to be smooth, or at least piecewise smooth. A smooth parametric curve means that the x and y coordinates of the parametric curve C, that is the f and g real functions of t, are differentiable, and so continues. And also the derivatives of f and g as to t are continues in the t1, t2, closed domain. Furthermore, the derivatives of f and g as to t are not simultaneously 0. That is, there is no t0, into the closed interval t1, t2, such that derivatives of f and g are both 0 at t0. If they are both 0 at point t0, it indicates a singular point where the curve might have a cusp or a sharp turn. At the given figure you can see the region under the parametric curve. Of course you have to assume that f of tv equals a, and f of tu equals b, for some tv and tu into the closed interval t1 and t2. From all the above we conclude that a smooth curve has no sharp corners or cusps nor discontinuity points. And so there exists a well-defined tangent line at every point of the curve. On the other hand, below we can see a curve that is piecewise smooth. Points x, 0, x, 1, x, 2, x, 3, are cusp or corner points, but the curve is smooth in each of the intermediate formed three intervals, x0, x1, x1, x2, x2, x3. Now going back to the parametric curve C, with f of t and g of t as the x and y coordinates respectively, with t, into the closed interval t1 and t2. Let us say that C is a smooth one. And we are looking for a real function, capital F say, with graph that corresponds, it coincides, to the curve C. In that case the area of the orange region should be given by definite integral of capital F function over the closed interval of A to B. Again of course we assume that f of tv equals to A, and f of tu equals to B, for some tv and tu into the closed interval t1 and t2. For this let us see if we could establish a basic idea, on which we will be based in order to determine function capital F. Now we have to see that every point, capital A, onto the parametric curve C, consists of a x-coordinate, x of t, equal to f of t, and a y-coordinate, y of t, equal to g of t, and parameter t into the closed domain, t1, t2. So now, let f be the continuous, differentiable, real function that gives the height, g of t0, of the parametric curve C, at every point f of t0, of x-axis. Also, one could put things in the following way, using more words. For every t0 into the closed domain, t1, t2, real function, f of t0 defines a unique point, x, of t0 onto the x-axis. This point in its turn defines a unique point A onto the parametric curve C. The y-coordinate of this point A, that is the g of t0, defines the height of curve C at x of t0 for every point t0 into the closed domain, t1, t2. So now we define a real function, F of x of t, to be equal to g of t for every t into the closed domain, t1, t2. Since curve C is smooth onto the domain from t0 to t1, F will be continuous and differentiable. Since F is a continuous and differentiable function on the closed domain, from a to b, then, the area of the region enclosed by the graph of function F, the axis of x, and the vertical lines x equals a and x equals b, is given by the definite integral of F function over the above closed interval. Now, to the above definite integral, we apply the integration by substitution method. We set x equals f of t. In this case d of f of t equals to the derivative of f of t dt. Also F of t equals g of t for all t in the t1, t2 closed domain. And below we can see the calculations that drive us to the wanted formula. In general, the new interval of integration, that is, t, v to t, u, occurs by solving the equation g of t equals to 0, if of course, a and b are the intersection points of parametric curve C with x-axis. And let's say t, I, where I equals to 1, 2, 3, and so on, are the solutions of this. Afterwards we calculate the f of t, I, for the various solutions t, I, in order to find the points at which curve C intersects the x-axis of x, y plane. If curve C is above x-axis with no intersection points with it, and we still want the area of the region under curve C, that is the area of the region enclosed by curve C, axis of x and vertical lines x equals a, x equals b, then TV, Tu are the solutions of the below written system. In our case the given curve C is a smooth curve since both its x and y coordinates are infinitely differentiable and the derivatives of f and g are not simultaneously 0. Furthermore curve C is closed since C of 0 equals to C of 2 pi equals 2. Also C is simple, since there is not two different values of t, v and u in the open interval, from 0 to 2 pi, such that C of t v equals to the C of t u. Now by using a table of values of curve C, we can very easily see that curve C is symmetric as to x-axis. This symmetry can also be seen by the coordinates of C. Since x of minus t equals to x of t, and y of minus t equals to minus y of t, for any t, into the 0, 2 pi, closed interval. Since this egg-shaped oval is symmetric as to x-axis, we only have to find the area of the upper region, and then multiply by 2. As we can see from the table, curve C intersects x-axis of the xy plane at the points b, 1, 2, 0. And b, 2, minus 2, 0. Now, in order to save time, please, see the way to follow, to find the integration endpoints. So finally, after some computations, and by using the previous found formula, we conclude that the area of the region enclosed by the given parametric curve is 2 pi. Now, as an exercise, try to find the area of the region enclosed by the parametric curve. C of t equals to open parenthesis cosine of t, sine of t minus sine of 2t, close parenthesis, and t into the closed domain, from 0 to 2 pi. In order to have a better understanding of the method, by which the intersection points of parametric curve C, with the x-axis occur, let us see once more the steps. We firstly solve g of t equals to 0, where g is the y-coordinate of the parametric curve C. So in our case we have sine of t minus sine of 2t equals to 0. From this we get sine of t equals to 0 or cos of t equals to 1/2. Below, we can see the next step. As you can see, we substitute to the x-coordinate of parametric curve C, the roots of the previous equation, g of t equals to 0. This substitution gives us the points of the x-axis of the xy plane, at which curve C intersects it. Since point 1/2, 0, occurs twice, we conclude that two different, opposite, scales of C, passes through it. That was one way, among many, to find the area of a region, enclosed by a parametric curve on xy plane. Two other, distinguished methods, we are going to deal with them later on, are: first, from the parametric formula to get a formula that connecting x and y. Second, by using Green's theorem. We shall deal with them in new videos. Thank you for watching.